Hello everyone, I am Anthony Thomas from University of Genoa, presenting our work Motion Planning with Environment Uncertainty in collaboration with Fulvio Mastrogiovanni and Marco Belletto. So uncertainties often arise due to insufficient knowledge about the environment, inexact robot motion, imperfect sensing, etc. Planning is therefore done in the belief space, which corresponds to a set of probability distribution over possible robot states or other variables of interest. So in this work, we consider landmark or object uncertainty, which will be explained later, and also the obstacle uncertainty. And since we plan under uncertain environments, it is imperative to compute the collision probabilities for safe motion planning. So object uncertainty or landmark uncertainty. So existing approaches assume that the landmark locations are known precisely. What exactly I mean by this? Let us consider a map of the environment obtained after a SLAM session. So in such a SLAM session, there might be a wrong data association or dynamic objects that prevent loop closure, and this can lead to wrongly estimated landmark locations. So the map obtained after such SLAM session might have the landmark locations uncertain. So I again stress the fact that we are actually considering an environment where this map is known, and we are planning within the known map. And we actually consider this, rather than ignoring this uncertainty, we consider this object uncertainty within the map. So let us understand this again. So on the left hand side, we have this figure. On the left hand side, we can see the object, so its location is precisely known, and then there exists a certain set of viewpoints from which the robot can observe the object. For example, if the robot has a laser rangefinder, then whenever it is within the object is within the sensing range, all such viewpoints produces an observation. However, the object location by themselves can be uncertain, as seen on the right hand side of the figure. So in such a case, we cannot say for sure where the object is. For example, the object can be anywhere within the blue shaded region, which is a 3 sigma uncertainty ellipse. Therefore, the viewpoints from which the object can be observed can also become uncertain. So in this work, we actually incorporate this object uncertainty in belief space planning and derive the corresponding Bayes filter in terms of the extended Kalman filter update equations. So as we can see, this is basically the mean and covariance of the robot location or the robot state, basically the mean and covariance. And these shaded terms are actually the extra terms when compared with the standard Kalman filter updates when we assume perfect landmark locations. Now we come to the collision probability aspect. So let us assume that the robot location is denoted by xk, and sk denotes obstacle location. Both are assumed to be, or both are actually Gaussian estimates. We assume the estimates to be Gaussian. So in such a case, the collision probability can be written as a double integral, while IC is the numerical integral. The IC is the indicator function, which is basically 1 when there is the collision between obstacle as well as the robot, and P is basically joint probability between the robot and the obstacle. Probability distribution between the robot and obstacle location. So there exists integral approximation methods which approximate this integral to compute upper bounds, or in some cases lower bounds. So where V is the volume occupied by the robot. However, we actually now compute an exact expression for this collision probability. So we derive the collision constraint in a different way by assuming that the robot and obstacle locations are tightly bounding spheres. So in such a case, the collision between spheres can be written mathematically, and where the norm square is basically less than the radii square, since both are assumed to be, both location and the obstacle location are assumed to be Gaussian. The difference between Gaussian is also Gaussian, and therefore we get a random variable y, which is W transpose W. Note that W transpose W is basically a quadratic form in random variable, and for a quadratic form in random variable, there exists an exact expression for the cumulative distribution function. And as can be seen below, basically the collision probability can be written as the cumulative distribution function of the random variable y, and therefore we actually get an exact expression of the CDF. Now we compare with other approaches. In the first case, we have the green denotes the obstacle, and the blue is the robot. In the first case, we have obstacle uncertainty. In the second case, we have obstacle and robot uncertainty. In the third case, we consider point like a robot and obstacles. And we compare it with approaches of Dudota and Burdick and Park et al. And to validate the value computed using our approach, we perform the numerical integral of the double integral shown before. And though this actually gives the exact value, and as we can see in all the three cases, our value is very much close to the actual value computed using numerical integral. However, numerical integration is of course computationally intensive and cannot be used for online planning. So to conclude, we have considered object uncertainty as well as obstacle uncertainty while planning, and we also compute the exact collision probability. Thank you.